Hello everyone, my name is Meng Chen, and it's my great honor to be here to introduce our work, Devil in the Room, Triggering Audio Backdoors in the Physical World. This work is done with Southeast University. Okay, nowadays, learning-based intelligent audio systems showcase prodigious speech communication capabilities and are widely deployed to security and privacy critical applications. For example, speech command recognition is used by voice systems to detect keywords or commands, and speaker recognition is deployed by many banks to authenticate customers. However, building a well-performed audio system is non-trivial. It usually requires thousands of speech data to train a powerful neural network model. Such a demand of high quality and large-scale data is not easy to meet. So it has been a common practice to adopt open-source data sets from third parties like USENIX and NeighborSwitch, etc. This practice saves the cost of data collection, but also puts the system within the risk of backdoor attack. In a backdoor attack, adversaries can poison the training samples by adding some specific triggers to the speech and changing their labels to some target classes. After training on such partially poisoned data set, the model will be infected and learn a hidden correlation between the trigger and that target label. So just like using the correct key to unlock the door, a successful backdoor attack needs to match the input trigger with the hidden backdoor. Actually, this indicates three attack objectives. The first is efficacy. The infected model needs to output the target label once the trigger is present in this input. And the second is specificity. The infected model needs to behave as well as the clean model on clean speeches. The third is fidelity. The poison samples with triggers should be similar to their clean versions so that the victim cannot perceive the attack. Actually, there are many audio backdoor attacks. They adopt different trigger patterns to poison speech, such as background noise, audible frequency tone, ultrasound, and even adversary perturbations. These triggers could activate the backdoor with a near-perfect attack success rate, like over 99%, but they are entirely generated and injected in the digital world. So in this work, we want a question. What is the case in the physical world? Can these digital triggers still survive in the physical world to activate the backdoor? To answer this question, we conduct a very simple preliminary study to play these digital triggers in a physical room and record the signals to test the audio systems. Consequently, we found that there's a significant degradation compared to their claimed digital attack performance. This is because the trigger signal is largely distorted, because the trigger is played by a loudspeaker, propagates over the air, and then recorded by the microphone. More specifically, the device nonlinearity and the noise interference will cause a mismatch between the trigger and the backdoor, so that makes the attack fail. So how to address this mismatch? Instead of improving these existing digital triggers, our basic idea is to find a trigger that already exists in the physical world. Specifically, we adopt the cello distortion itself as a physical trigger. We choose room impulse response, RR, which characterizes the sound reverberation in a room as our physical trigger. We choose it for several reasons. First, it's a form of natural sound distortion so that there is no need of device for injecting the trigger signals. Second, the trigger is carried by the reverberation, so it's less affected by noise. Third, it's very natural and not easy to distinguish it from reverb speech. Based on this, we hope to match the trigger with the backdoor again, even in the physical world. But can speech models really learn the RIR pattern well? To validate this, we do a further experiment. We poison 10% of the training data set of some speech models and changing their label to a target class and test the speech models. So during the training process, we observed the loss curves converge very quickly, and we found that the in-fact model can successfully build a correlation between the R trigger and the target label, as we expected. Now we have validated that RR can serve as a physical trigger, but applying it in the real world attack scenarios still faces several issues. First, the adversary cannot enter the target room to measure the specific RR. So we need to determine how to retrieve the RR signal without on-set measurement. Second, convolving with R signals will induce reverberation to the speeches. So how do we perform stealthy data poisoning during the pipeline of an audio system? Third, reverberation is everlasting in the room. So how do we precisely control the backdoor activation without affecting the normal functioning? To address these issues, we first pre-train a generative model to generate RR signals as our triggers without any on-set measurement. This generator is based on an encoder and decoder architecture, which encodes the real RR signals into latent features and then reconstructs it back to RR signals. This generation process is conditioned on acoustic parameters. These parameters characterize the reverberation property of RRs, including room dimensions, the location of the adversary, the location of the audio system, and the reverberation time of the room. We train this generator on a large-scale data set to learn the RR distribution, and then we can generate RR triggers with the specific parameters of our target room. Next, we head the data poisoning operations into the data augmentation process. This is a common step in the pipeline of building an audio system. We follow the same step as the normal data augmentation steps to normalize the trigger, convolve it with speech, and then assign it a target label. Finally, we apply a pair of triggers to realize the fine-grained control of our backdoor activation. The positive trigger uses the RR of the target room to band the backdoor with a specific word or specific speaker, while the negative trigger uses random RRs to keep the reverbed speech correctly recognized. By optimizing this objective, we can implement a backdoor to the speech recognition or speaker recognition models, and then the adversary can activate the backdoor physically and stealthily. To evaluate our attack, we construct experiments on 3 speech command recognition models and 3 speech character recognition models, and we compared our attack with 5 baselines. First, we test the efficacy and specificity using recorded speech. The results here show that digital triggers either degrade the benign accuracy on clean samples or fail to activate the physical backdoor. In contrast, our attack can achieve attack success rate over 90% and remain the benign accuracy of the infected models with only a drop of 3%. Then we also perform objective and subjective evaluations on the poisoned samples in terms of attack fidelity. In the objective evaluation, we can see that our trigger induces more less distortion than other digital triggers. And in the subjective evaluation, we found that existing digital triggers can be easily detected by human listeners, while almost 80% of human listeners cannot detect our triggers, since it just sounds like a reverberation and is very natural. We also investigate some factors that investigate their impact on our attack. We found that the poison rate can be further reduced to 5% with a good performance, and there is a negligible impact of different targets on the performance. We repeat the attack at different locations in the room, and found that the attack can reach an effective distance of 5 meters. We also observed that some high-end microphones used by the audio system need to higher attack performance than cheaper ones due to their better device energy. In addition, we have recruited some volunteers to launch the attack with their live speech. The results demonstrate that it's very practical to perform a live speech attack in the real world. We also investigate some different levels of defense methods to mitigate this attack, including source level liveness detection, data level trigger disruption, and model level backdoor defense. Due to the time limit, I will not talk about this. You can find more details in our paper. So let's conclude this work. First, sound channel distortions causes digital audio backdoors attacks fail. We validated that device nonlinearity and noise interference cause mismatch between the trigger and the backdoor. Second, channel distortion itself can serve as a physical trigger. We propose a RR trigger to activate the physical backdoor. Third, we design a systematic method to launch this audio backdoor attack and demonstrate it in the physical world. Okay, that's all my presentation. Thank you for listening.